Here we want to take a look at directional derivatives and gradients. So let's formulate a definition for directional derivative. Here we have a surface, z is f of xy. We've got a vector, u, that gives us a particular direction. Now I've drawn another line parallel to u, in other words, as the same direction as u. And so we want to take a look at a point P whose coordinates x0, y0 are in the domain of f. So we want to take a look at the derivative in the direction of u, where the u is given as a unit vector. So mostly the vector u has direction. Now, one unit vector is just the vector cosine theta sine theta. We'll use that for developing our ideas, but we can replace that with any unit vector. Now, I've drawn here a vertical plane through the point P and labeled the coordinates of the points. The point P is x0, y0, and whatever you get when you plug that into the function. And then we're using the point Q to mean any other point in the direction of u from P. Now the black line that you see here around the surface that's in the direction of u, we're referring to as the curve C. And so we're just recognizing that when we talk about the slope of the surface in the direction of u, we're really talking about the slope of that curve at that point. Now you see here I have identified the vector PQ as simply being the difference in the x's and the difference in the y's. You can see here what those are: x minus x naught and y minus y naught. That's the vector PQ. So the vector PQ is some multiple of the vector u, and the vector u was cosine theta sine theta. So the vector x minus x naught comma y minus y naught is some multiple of the vector cosine theta sine theta. And multiplying that out, we get x minus x naught is t cosine theta and y minus y naught is t sine theta. So we can write x and y in terms of the point x naught y naught and the vector cosine theta sine theta with some parameter t. Now here is the slope of the secant line between those 2 points. We're going to plug in for f of xy and f of x naught y naught what we just found. So here's the f of xy and here's the f of x naught y naught. That is the formula for the slope of the secant line, again in terms of the point x naught y naught, the vector cosine theta sine theta, and some parameter t. Well, if that's the slope of the secant line, we can do the limit of that as t goes to 0 and get the slope of the tangent line. So this is where the definition of the directional derivative comes from. Now, again, if you follow through the ideas and computations that we just did and look at this, this is a similar version to what we did in Calculus 1. The definition of the derivative is the slope, y2 minus y1 over x2 minus x1, slope of a line, So that is the definition of the directional derivative. Just like in Calculus 1, however, we won't be using that definition very often, but I will illustrate it for you. So here's a function that is given by f of x equals 4 minus x squared minus y squared. We want to take a look at the derivative in the direction cosine pi over 4 sine pi over 4, which would be angle of pi over 4, at the point 1, 1, and 2. So from the definition, this is what we would have. So here is our x naught plus t cosine theta. Here's our y naught plus t sine theta. We plugged all of those into the f of xy. 4 minus x squared minus y squared. We subtracted the original function and divided by t. Looks familiar. I think that's what we did back in Calculus 1. Then we will do all of the algebra for that. We will square these terms, combine things together, and simplify. Now, doing the limit of this as t goes to 0, we would need to factor out the t's and cancel, and then substitute the 0. So there is what we call our directional derivative at that point and end that direction. Now let's change this up a little bit. So here is what we used in our definition for our directional derivative. We're going to refer to this function as the function g, and notice g is a function of t. So we're going to do the chain rule on this like we did in the previous section. So we get, by the chain rule, the derivative is the partial with respect to x times cosine theta, the partial with respect to y times the sine theta. So maybe we could use this instead of that definition. So let's try this from our newfound formula instead of from the definition. So we need the partial of x, the partial of y. Now we'll be needing to plug in our values of x and y to get numbers. And we substitute those in. Here's my partial of x. That's negative 2 times 1. That would be here. Here's my cosine theta. That's cosine pi over 4. Here's the partial of y. And the sine theta. That's the sine of pi over 4. We substitute the 1 for x and the 1 for y in that formula, and then do the calculations. Now again, I think that's a little handier than having to go through the definition. So we found out that this is a little better working definition for our directional derivative. Now, the u, remember, is any unit vector. So we don't have to use cosine theta and sine theta. In other words, we don't have to find the thetas in order to use this. But we do have to have u as a unit vector. However, notice this formula, partial of x cosine theta, partial of y sine theta, where cosine theta, sine theta is u, is nothing more than the dot product of the partial of x, partial of y times u. So this would be a nicer working definition for our directional derivative. So let's try that working definition by doing the directional derivative of this. So we'll do the partial of x and the partial of y. Now our direction vector is not a unit vector. So in order for us to use this, we got to turn that into a unit vector. The magnitude of that would be the square root of 3 squared plus 4 squared, which would be the square root of 25, which would be 5. So here's our unit vector that gives us our direction. Well, the definition says we need to do dot product of those two. Now we can do this dot product, come out with x's and y's. However, again, we know our coordinates for x and y, so we could plug those in place of the x's and the y's. Then do the dot product. Okay, so here's our definition of directional derivative. Now we're saying u can be any vector. We don't have to have cosines and sines, as long as that is a unit vector. Now again, we just talked about how this is the dot product of the vector created from the partial of x, comma, partial of y, and the unit vector. Now this vector has a special name, and that's called the gradient vector. The little upside down triangle is read grad or del of f. And again, that simply means the gradient. So here is a shorter, easier to remember working definition of directional derivative. Now there's some interesting ramifications from this definition of directional derivative also. The angle between grad f and u, if we call that theta, tells us that we could write our dot product as the magnitude of the grad of f times the magnitude of u times the cosine of theta. Well, remember, u is a unit vector, so the magnitude of u is a 1. And if we take a look at this, notice that cosine theta can only have values between -1 and 1. The largest value of this dot product would occur when the cosine of theta is 1. And so that's kind of a special situation. And so the definition of the directional derivative, grad f dot u, tells us that the grad f part of that gives us the direction of maximum increase. So we don't even have to do the directional derivative. We just need to do the gradient. Also, the magnitude of that gradient tells us the maximum value of our directional derivative. So again, everything that basically we need to answer from directional derivatives, other than what is the directional derivative, could be answered from just that gradient vector. So let's try a few examples and see what it looks like. Here we've got the function x sine yz. We want to know the directional derivative in the direction of 1, 2, and -1 at the point 1, 3, 0. So we'll do the partials. Here's the partial of x, partial of y, partial of z. That's our gradient vector. We'll substitute the 1, 3, and 0 for x, y, and z. So this is our gradient vector at the point 1, 3, and 0. So the vector 1, 2, -1, which is our direction vector, is not a unit vector. We need to find the magnitude of that and turn it into a unit vector. Also, you could do that on TI-89 using the unit vector command, and then do the dot product of those. Now, this is easy enough to do by hand. Since the first two components are zeros, we just get 3 times -1 over square root of 6. So that's our directional derivative. Here we're given the function z equals xe to the y, and we're asked to find the direction that we're going from the point 2, 0, where we have a maximum rate of change. So if this is a surface, and we're standing on that surface above x equals 2, y equals 0, the question is, where is it the steepest? Which direction would we go and have the steepest, the maximum change? So we'll do the gradient. Now again, that's the derivative with respect to x. That would be e to the y. The derivative with respect to y, which would be x e to the y. Substitute to the point 2, 0, and we get our gradient at the point 2, 0. So we're basically through. The gradient vector is our direction of maximum rate of change. So the direction is 1, 2. Now, we may be asked for that in terms of what some of the angles are, so we'd still have work to do from back in chapter 2 to find angles if we were looking for angles, but that is a direction of maximum increase. And if we do the magnitude of that, the square root of 5 is the maximum increase. So that's the largest increase in this whole function. In our final example, we're given a function for the temperature at a point in space. Here's the function, t equals 80 over 1 plus x squared plus 2y squared plus 3z squared. And we're asked which direction would we have the maximum increase in temperature. So where's it the hottest? So again, we'll do the partials of x, y, and z. Go ahead and plug in our numbers. And we already have our answer. There's our direction